I can still remember the sound of the ice cream van. So I was being taken to the zoo in a town called Zug in Switzerland. In the middle of the town, there was a park. In the middle of the park, there was a zoo. In the middle of the zoo, there was this kind of enclosure where there were 3 elephants that you could go on a ride on. And so 2 of the elephants were for grown-ups and big kids, and they had a kind of blanket on the top with rope handles. And one of the elephants was for little kids, and it had a kind of wooden castle with benches inside that you could sit in safely. But of course, I was 6 years old. I wasn't a little kid. I wanted to go on the big boy elephants. And so after, no doubt, some discussions with my parents, I was put up on the back of one of these elephants. And so I'm sat there with my legs open and I'm holding onto the rope handle. And I remember looking behind me at the little kids on the wooden elephant thinking, look at them on their silly wooden elephant, whilst I was happy as Larry on mine. Until, that is, the elephant started moving. So it takes a big step forward and the blanket just whoosh backwards, and at the back I end up hanging off of the back of the elephant. And so I'm kind of there holding my own body weight, and if I look forward, it's just my nose to the elephant's arse. And then the elephant slowly starts moving around this enclosure in a circle. And it goes all the way around, twice. And by the second time, my little arms, I'm 6 years old, my little arms are just giving out. And I start to think, well, I can't hold on anymore. And I look down to think, okay, well, where would I fall if I had to let go? And all I can see is the big feet of the elephant behind me. And I don't know if you remember a similar moment, but for me, this was, I think, the first time as a kid where I really suddenly felt fear as an emotion just cut through. And the moral of this story, coming back into the room, is that nothing stands still. And if you look at state transfer, where one of the core concerns of web and application development, how do you transfer the data between the back end and the front end? It has evolved from these older ad hoc manual data fetching imperative systems towards more systemic declarative approaches that are built on sync and local data. And as we've gone on that journey as an industry, the experience of using software has been completely transformed. You've gone from click the form button, watch the loading spinner, make a cup of tea, come back, to this new grade of really high quality modern software, systems like, say, Figma and Linear. So these are 2 applications that have really gone on to dominate their software categories. So Figma, design software, Linear, project management software. And it's precisely because of the quality of user experience they've been able to deliver because they're built on sync. For Figma, it's about collaboration. It's a multi-user system. You have to keep the data in sync, the local data that people are working on, otherwise they're working on stale data. And with Linear, they use sync to craft just this really fast, modern experience. It just feels instant to use. And the key thing about that is you have to get the network off the interaction path. Otherwise, you just can't make apps that are reliably fast. So if we come back here to Phoenix, how do we build this new grade of modern, fast, collaborative applications on Phoenix. Well, one way of building collaborative apps is LiveView, which is awesome, but LiveView fundamentally has the network on the interaction path. That's how it works. And so if we put LiveView to the side just for one moment, because we'll come back to it, and we look at the other primitives that Phoenix has for building real-time applications, you have sockets, channels, PubSub, you have Presence, which is built on CRDTs, you have Absinthe, which builds on PubSub to feed data into GraphQL subscriptions. And of course, under the hood, we have OTP, so we have actors and servers and messaging and so forth. And so if you look at this, compared to any other framework, it's a pretty rich set of real-time primitives. And so you may think that we have the building blocks here to build real-time apps on Sync. And in a sense, you do, right? If you look, this is LiveView code, and it could just as easily be a controller with a WebSocket. And basically, you establish a PubSub subscription in the mount function. There's an event to handle user input, and we then broadcast the changes to the other users. And if you are trying to build an application that is syncing data into the client between multiple users, this will give you a real-time app that demos really well. But if you're using it to keep that data in sync in production, it will fail. The thing about Sync is it is a bit like crypto. It is full of fascinating engineering challenges, but it is really hard to roll your own. So if we just dig into it a bit, let's say we have a Postgres database, we're consuming a change feed into Phoenix, and we're fanning that out to clients. And we want to keep a subset of the data in the database in sync with local data in the client. So let's start with the first part. In the case of Postgres, you can stream out of a logical replication publication, presumably then through some sort of message processing pipeline, gen stage or otherwise. And so if we just look at this and try and load up on some of the complexities, are you syncing all the data in the database? Or are you syncing a subset? And if so, how do you get the right data in the publication? Now, the connection between the two is probably pretty good on the back end, but it can still drop. So what do you do when the connection drops? And what happens when you deploy your Phoenix application? Or what happens when you migrate your database? Or what happens when there's a bug in your Phoenix application? So if in this case the Phoenix application stops consuming the logical replication publication, the write-ahead log in the database would just back up. And then you get to a point where either the database storage fills up and your database stops working, or you start having to throw away the data. And so, I mean, this first step is relatively easier than the others, but already we start to see that there just are these kind of operational complexities when you're trying to run this system reliably in all eventualities. And if we now look at the second part, which is filtering the data, mapping the right data to the right client, and fanning it out to the clients, so how does that work? For example, how do you do the routing or the kind of mapping of the data? Are you maintaining a secondary index to look up things like this data belongs to this user, so therefore it should go to this client? Or are you querying back to the database to get things like user roles and memberships? But if you're querying back to the database, you can't query Postgres at the same snapshot as the transaction that you're processing on the replication stream. So I'm just scratching the surface. There's a whole bunch of these types of considerations. The real key thing here is the difference between broadcast and sync. And so if we come back to this real-time code we were looking at before, this is broadcast. It sends the messages to the connected client. But what happens if the client isn't connected? Well, it then needs to re-query when it reconnects to make sure that the local data is up to date. And that means you're either looking at stale data or you have the network on the interaction path. And so to avoid this, to build on sync, you need to be able to trust your message delivery. And so in the Beam world, here, maybe this wouldn't be so hard. We have process inboxes, back pressure, mechanisms for this kind of thing. But we're not in the beam. We're doing exactly once message delivery across the public internet into clients that we don't control and we can't trust. So for example, say you're trying to tolerate patchy connectivity between the client and the back end, and you're maintaining some sort of message buffer, like that back pressure mechanism. Well, we saw before that the database fills up if the back end disappears. Believe me, the back end fills up 1,000-fold when your clients start disappearing. So there are just some fundamental and serious engineering trade-offs here between exploding resource use on one side and inconsistency in the client data on the other. But we haven't even got to the hard problem yet. How do you handle local rights? Eventual consistency, conflict resolution, rollbacks, preservation of user intent. So Sync is full of fascinating challenges, but if you're just trying to get something done, if you're trying to build your app, you don't want to have to go into this rabbit hole and roll it yourself. What you're looking for is you want to look to your framework to solve these concerns for you. And so that's why last year this was one of the themes of José's keynote, with his vision of adding Sync to Phoenix. And he built it. He published a prototype and a design document, and we were discussing it with him, and it was clear to us that when we dug into it, there was a huge overlap between José's vision for Phoenix.Sync and what we were already building with Electric. So Electric is a Postgres sync engine built in Elixir. It takes data out of Postgres, it filters it, and it fans it out into local apps, web apps, mobile app services, any way you want. And we do this we do partial replication, so we replicate subsets of the data. And we have a partial replication primitive called a shape, which is that subset of data. And importantly, we work with any Postgres, any data model. There's no limitations on data types or features or constraints or anything. And we work with any web stack. And in fact, it's specifically designed to sync data through existing back-end frameworks. And so we got together and we discussed, can we build Phoenix.Sync on Electric? And we looked at the integration path and the API designs with both José and Chris. And we changed the Electric code base, the way it was organized and packaged. So Electric has always been open source Elixir. It's Apache 2, but we were building it as a standalone service. And so what we did was we changed things so that Electric can be integrated as an embedded library dependency of your Phoenix application. And then we wrapped it up with function APIs and macros that work with Plug, Phoenix, LiveView, etc. And so I'm very proud and pleased to introduce the work today, which is Phoenix.Sync. So it's published on Hex as Phoenix_Sync, and you can all use it today to build apps on Sync using Phoenix. With all of that complexity I talked about before solved for you. In a way that just works and scales out of the box. So for example, here we're showing scaling a read path sync workload out to 1 million concurrent clients. It's a total of 80 gigabits per second data throughput. We're doing this on a single Elixir app using a single commodity Postgres, and it's flat memory and it's flat compute use. So this is not a prototype system. This is a production-ready system, and it's now built into Phoenix. So let's unpack how it works. Let's take our diagram from before, focus on the first part, reliably consuming changes from Postgres and piping them into existing Phoenix primitives. So what does that look like? Well, at the lowest level, there's an Elixir client. And so what this does is it takes an ecto query. In the first example, it's just the ecto schema. Second example, it's an ecto query. And it turns it into an Elixir stream. So what actually happens there is it will query Postgres for the data that matches the query initially, and it will stream that through the stream. And then when any data changes in Postgres that would be in the query results, it streams those through too. And then you can feed that stream into anything you like. PubSub, Absinthe, etc. But particularly, there's a really nice tight integration with LiveView, and specifically with Phoenix.LiveView Stream, which is the existing way of efficiently streaming insert, update, delete operations into a LiveView for large collections. So if we take an example, this is a LiveView, should be very familiar. You have a mount function where you're setting up a stream for all the to-dos. And then we have a handle event function, which is taking a user input to add a to-do, and where we just write the to-do to the database, and we put it on the stream. And so this stream mechanism, as opposed to just assigning the list, the key difference is that the server side doesn't have to keep the whole collection in memory. So this is the way that LiveView has, which is really cool, for working with larger collections without having to keep them in memory on the server for every client. And what we do with Phoenix.Sync is we just swap out that existing stream function for sync stream. And it's done. It's 5 characters, and you now have a real-time multi-user LiveView app where every user's LiveView is automatically kept up to date with the state of your Postgres database. So you don't need to put the to-do. So you don't need to put the to-do on the stream, you just write it to the database and it does it for you. And LiveView is handling the reactivity between the backend and the client, but Phoenix.Sync is handling the reactivity between Postgres and the Phoenix application. And so that gives you an idea of one, that's how you can do this first part of syncing into the back end. But what about 2, right? Syncing all the way into the front end directly. And that's where the design of Electric just really shines, because Electric is designed to sync through your existing back-end API just using old-fashioned HTTP and JSON. We deliberately do this sort of clever sync stuff through old-fashioned long polling, because that allows us to scale out the data delivery through existing CDN infrastructure, which is what allows it to be so resilient and scalable out of the box. But also what it means is that you can sync data through an existing back-end web framework. So through Phoenix Router, plugs, controllers. And so what we do is we provide a sync macro that exposes a shape, our replication primitive, through the Phoenix router. And so what you can see here is a plug pipeline, and then we have a scope where there's a sync macro which is exposing an ecto query as a shape stream. And really importantly, what it shows you is you can do authentication and authorization of access to data that you're syncing just through your existing plug middleware. You don't have to codify your access rules into something like RLS or a rule system in the database to do sync. You can just do sync the same way that you would a normal web API endpoint. And so this is actually defined at compile time. So there are limitations on what you can specify in the sync macro in terms of the ecto query. And if you need more flexibility in building a query at runtime, you can drop down to the sync render function in a standard controller. So this is just a normal Phoenix controller. And as you can see, it's using the assigns, which would be set, say, by your plugs, to build a query that means you sync just your to-dos. So again, it's sync where the authorization is completely under your control in Phoenix, and you can construct arbitrary shape definitions in your runtime code. And then in the client, you just bind data to your components, and it's automatically up to date. And you can sync into anything you like. You can sync into state variables in memory. You can sync into databases in the browser. Which brings me to the third part. How do we do writes? And the answer, which you may have figured out by now, is we just use Phoenix. So LiveView events post to a REST endpoint, changes made to Postgres through Phoenix get automatically synced back out and everything stays up to date. But of course, the wrinkle is that you can't have the network on the interaction path. And so you need to layer on a client-side solution for making instant local writes that display optimistic state whilst the write is syncing in the background. There's a whole bunch of different client-side tooling you could use for this. It's this kind of thing. This is now built into React Core. They provide a use optimistic hook. It's a very common pattern that basically allows you to apply an instant local write, show optimistic state, and then when a promise resolves, it discards the optimistic state for you. Or for a more sophisticated approach, you can use a front-end framework like TanStack. So TanStack is a very popular mainstream library for building front-end apps. It gives you managed queries, mutation primitives, reactive store signaling, etc. And TanStack, as of this week, now has a very, very cool new library called TanStackDB, which was built to be compatible with Phoenix.Sync out of the box. So this is their data flow diagram. It's based around syncing data into collections as a primitive. And then the collections you bind data with live queries into the components, and then your components, when you make writes, it has this tight inner loop where you just instantly apply optimistic state, but then you have mutation functions which handle how you send the data to the server, and then when that syncs back around, it discards the optimistic state. And as I say, it's designed to work out of the box with Electric and therefore Phoenix.Sync. And so when you configure a collection, here we're just syncing data out of that sync macro in our Phoenix router that we defined before. And this is just the whole configuration to basically keep the results of that shape live in a collection in TanStackDB. And then just to show you, this is how you do live queries to bind the data to your components. So whenever the data in the collection changes, the results change and the component re-renders. Now, as it happens, there's some very, very cool stuff behind this. This is implemented on a TypeScript implementation of differential data flow. So you can do complex cross-collection queries with joins, aggregates, etc. in the client, and they all and the queries are always sub-millisecond. So you don't have this problem where you have an embedded database, the data changes, you rerun the query, where for complex queries that can actually take a long time. In this case, it's extremely efficiently, incrementally maintained, and the results are always just like looking up straight out of an index. But I digress. So what we wanted to do is focus on writes. Yeah? So how do you do writes with TanStackDB? Well, this is very canonical front-end code. This is how you do it with something like React Query. And in this case, instead of use mutation, you have use optimistic mutation. And you provide, that creates a mutator, which is the transaction variable here. And when you create the mutator, you provide a mutation function which sort of handles the background sync. And just in the foreground, when you're inserting the to-do into the collection, it's just applied instantly as local optimistic state. And all of the sort of machinery around that is just abstracted away and handled for you as a developer, so that's all the code that you need to write. And then this is an example of a generic mutation function which just takes any changes that are made to any collections and posts them to an ingest endpoint, which can be in Phoenix. And so with Phoenix, you can just then take that payload and write the changes into the database. And the Phoenix.Sync module has a writer module that provides helpers for this. So one of the tricks is that if you do this and you return the transaction ID that the changes are applied under in Postgres, then the front-end machinery monitors the replication stream for that transaction coming back in, and that's when it discards the optimistic state. And that's actually a smart way of doing it because it allows for concurrent changes from other users for you to rebase your optimistic state on top of them until your transaction syncs through. But the real power of the writer module comes from a declarative ingest pipeline. So again, you can just have a single ingest controller, and you define this, you do this writer.new, and then you pipe it through a series of allow and then apply calls. And that takes care of just returning the transaction ID for you. And if we zoom in on it, so here what we're doing is you're saying for every ecto schema that you want to be able to ingest changes for, you have an allow call. And here we're saying, okay, so we're going to ingest to-dos and to-do lists, and you can have as many schemas as you want. And typically, you only need one of these pipelines with just a generic, like a single controller, to handle all the writes coming into your app on this write path sync model. And then this pipeline is designed to allow you to reuse your existing plug and ecto change set logic for authorization and validation. So you don't actually need to change the way in which you're, say, currently handling writes. If you're authorizing them through something like LiveView or a controller, you can just configure that logic to be run as part of this pipeline. So in this case, for instance, there's a number of these sort of steps in the ingest kind of pipeline, but check just validates the input parameters without touching the database. So it's an efficient step that you can just sort of discard rubbish with. Load then allows you to load the context. So if there's like an existing to-do with that ID, for example, but it also allows you to, if it returns nil, then it's treated as unauthorized. So this is where you can just basically do any ad hoc authorization logic to say, okay, is this user allowed to perform this action on this resource? And a validate step is just an ecto change set function. And in fact, if you look at the to-dos.list, the defaults for these are check is a no-op, load just loads the existing resource if it exists, if it's an update or a delete, and validate just uses the default change set. So you can extend this, and you can override, and you can configure any logic you like, but also it's just very dry. And it basically allows you to ingest these changes using your existing plug and change set logic for authorization and validation. And so that's it. It is genuinely sync solved. Shall we fire it up? Okay, so I need to talk you through a few steps. So first of all, as Jim said, this is going to work a lot better if you're on the Wi-Fi. This is a crazy audio demo, and we do time synchronization code, and mobiles are crap for that. So the Wi-Fi code is 2016, I think, right? So if you scan this code and open it, you should get to a web page, and it'll take a moment, and then a start button will come. And if you click start, you should get to the point where you see a speaker. The first step of the demo is going to be a sound check. And so for that, I need to ask you, please, make sure your phone is not on mute. On some phones, it's on the side, right? There's a little control. So make sure it's not on mute and turn the volume up to maximum. It's a big room. We're doing this with mobile phones, so max the volume, please. Anyone need this QR code? Can I jump off? Who's on? Do we need the Wi-Fi code? Wi-Fi is... Yeah, you got it, yeah? Okay, cool. It'll take me a little while to set up, so sort of carry on. You should get to the point where you see a speaker. Okay. I need to get... So I'm trying to get my screen on screen, but we're having problems with the screen thing, so I'm not quite sure how to do it. Basically, I'm only just going to enter a couple of commands up here, so I guess I'll just explain them to you. The first thing I'm doing here is I'm just PSQLing into a Postgres database, and I'm just going to do inserts. So I'm literally typing insert into sounds, the name of the sound. And what that's going to do is, this is set up with the LiveView integration. So we write to the database, and we've set up a Phoenix.Sync LiveView sync stream into a LiveView, and then that's just pushing the data through into a LiveView that you're all connected to, and then we just have a little Phoenix hook JavaScript to play the sound. So I'm just going to hit this now, and let's see if it works. That was the elephant. That was less than I thought. Are people having problems? Do we have volume? Can we do another one? Max the volume. Try and get on the speaker page. Let's see it again. Okay. I have another one. Just that. And Now this is the sound of the ice cream van. So I'm now just sending a instruction, which has just hit a problem with okay, I got a live bug on the demo. Keyword value must be followed by a space after ENUS. So my env language is wrong, which is totally weird because I've just run this previously. I'm just going to exit and reconnect in case this fixes this. Sorry, let me try again. Okay, you should have maybe been taken again to a start screen. So if you do, could you please, when it's activated, click the start button, and then what that should take you to is a screen with an empty rectangle. No, that'll take you, sorry, to a screen to select a track. And so in this, you can normally select a number of tracks. I've just got one track that you'll see there. It's pre-selected, so at the bottom of the screen when you get there, if you just select it, so the track's called Tequila, and then you'll get through to hopefully an empty rectangle that says no data on the bottom. How are we doing on that? Okay. Woo! I'll just give you 5 seconds if anyone's catching up on that. And then what I'm going to do here is I now run a mix task, which is going to do something a bit crazy, because I thought, well, let's see what we can do here to demonstrate the stack. So I'm taking an MP3 file, I'm loading it, and I'm turning it into vector data. I'm writing that into a PG vector column inside Postgres, because this is the AI age, and this is what we build nowadays. And then the vector data is being synced through Phoenix.Sync into a front-end application, where it's getting repassed back into audio data, and then that's being played by the web audio API. And there is some time synchronization code that's been going on in the background that hopefully is synchronizing your clock. So we're going to try and see if we can play back a track in sync together. And the difference between this and the previous demo is that what we're going to do is I'm going to run this command, and it's going to sync the data in locally, so you have the data inside your app. And then I'm going to schedule some stuff so that we do it, but basically you could just use that data locally. So this is the kind of front-end sync paradigm. So let's give it a go. I'm going to run mix populate. Sorry you can't see it. 3, 2, 1. And that's written the data to the database, and we are maxing the conference Wi-Fi. And does anyone see anything on their phone? What's going on there? We got error? This totally worked in the US, but there's 400 people here. And that's really disappointing. No. Yeah, I'm seeing errors. Say again? You can see the error, right? Yeah, what does it actually say? Start the app, in theory. Yeah, okay. Let me just give it a go. Maybe you can help me debug. Yeah, I'm getting... You can restart the app. Just kill it, start it again. I think it's too many. I think we just have... It's just a dev server that I'm running on a box, and I think we've killed it. Oh, you got it? You got it? Who's getting data? Hooray! Okay, hold your phone up if you've got the data. Is that refresh? Okay, is it coming through? Thank you. Oh, it's erroring again. You shouldn't be able to do that. Okay, I'm going to just have a go at sending the instruction to play together. Oh, I worked so hard on this. Okay, that was really disappointing. I'm sorry about that. So what should have happened is you all sync the data locally, and then I would have been in position to schedule. There was a countdown, and we all played it back at the same time. I have no idea what was going wrong. There were all sorts of tracebacks running through there. I blame probably my deployment of the application, which was just a dev instance on a box somewhere. So apologies for that. What we can do, though, is at the end of that, the idea was that we all said tequila at the same time. So if we just imagine the end of the song, da 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 da. Da 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 da. Hey, thank you. So if I recap, right, we have loaded up on why apps are being built on Sync. We have talked about why rolling your own Sync is hard, how we've integrated Sync into Phoenix, both for LiveView and for front-end apps, how you can do right path sync, local writes with optimistic stay, and we failed the demo. And so you might think that the talk ends here, but it doesn't, because nothing stands still. Not application development, least of all JavaScript tooling. And even whilst we've been building this integration, the world has changed. The elephant has taken a step forward. So if these examples I was showing earlier, LLM started writing code. Instead of building apps with Figma, people are building apps with Lovable. And the code itself, the type of apps that we're writing and creating, is just changing around us so fast. From you have this now older generation of what we used to build around SaaS and enterprise software, etc., to these new systems which are AI apps and agentic systems. And when you scratch the surface on these AI apps, you get actually this whole list of factors that all steer you into building them on Sync. Resilient token streaming, resumability, interruptibility. So just to show you, for example, this is ChatGPT. This is how it works. It streams the tokens in from the model to the front end and writes them out for you. But any kind of glitch in this, like here we just turn the network off, it just breaks, because they're streaming directly from the agent into the front end. Whereas if you architect these apps on Sync and stream into a store, well, as we know, we have reliable, resilient message delivery into the front end. So just for example, this is the same thing built on Sync. So this is streaming from the OpenAI API in the cloud into Postgres and through Phoenix.Sync into the front end. And in this case, if there's any connectivity issues, if the user refreshes the page, etc., the data's all there and it just resumes seamlessly and there's no problems. And as I say, there's like interruptibility, and you also have like what happens when the user's got two tabs open or it's multi-device. And so there's a whole bunch of these sort of AX and basic engineering reasons why you would build AI apps on Sync. But the fundamental reason is teased in that linear for agents screen, because the key difference is that AI apps are fundamentally collaborative. There are at least two users. There's the user and the agent. And so if the agent is doing stuff, it's going to be updating state. And you need to keep the user in the loop on that. And if the user is doing stuff, they're updating state, and you need to keep the agent in the loop on that. But of course, it's not just one agent. The whole point of AI is that you can spawn lots of them, swarms of them. And if this is how we are actually all going to get stuff done through software, then it's not just one user in an AI session. We're going to need to collaborate on those sessions and those workflows. So you don't just have one user in an AI session, you have lots of them. Multiple users, multiple agents, collaborating on getting stuff done. And so if we see what that looks like, this is a multi-agent, multi-user chat app built on Sync, where the shared state that the agents and the users are collaborating on is tasks in the form of a to-do list. And so one agent on the right is told how to create and monitor a to-do list, and then the agent on the left is told to make a project plan. And then as they're doing this, the user on the right navigates to take a look at the to-do list. And so the to-do list, the state, it needs to be live and up to date in the local device for the user and in the cloud for the agent. And then the left-hand agent is told to distill the plan into tasks and then add them to the list, and the agent on the right detects the tasks and starts performing them. And so as you can see, the users and the agents are collaborating on the same state. And if an agent completes a task, the user needs to know. If the user deletes, pauses, interrupts, reschedules something, the agents need to know. And I'll stop the demo in a sense. You get the point, right? It's not just enough to have collaborative state in the cloud. You also need to have it synced into the local user's device so that you keep the user in the loop. And as this moves into this next phase with multiple users and multiple agents, I would rather be kicked in the head by an elephant than to do that on manual or ad hoc data fetching. It just doesn't make sense. And so that's why Phoenix has added sync. It's not only so you can build fast, modern, collaborative apps, but also so you can build this next generation of AI apps and agentic systems. So this big transformation in software development that is just changing our industry and maybe all of our livelihoods isn't something to fear. Because with Phoenix.Sync, you can build these types of new systems with the skills and the tooling that you already know and love. Thank you. Very happy to, yeah.
Yeah, okay, let's take a couple questions. Any questions here? Anyone? I've got one. So the sync, if I remember from José's talk, it's streaming what's going on with the Postgres database to the Phoenix app, correct?
Mm-hmm.
So there's filtering, you talked about filtering that would go out to, let's say, the client. Is that filtering done now still at the application layer, or is it done at the database layer?
Nothing's done in the database layer. There's no load added to the database. All the load is taken off the database. The Electric system does core filtering of shapes. So it consumes the logical publication feed, and it's mapping the changes that come through that to the right shapes. And we actually have shape logs that we cache on disk. And then those shape logs are served through Phoenix out of the Phoenix router. And that means that you can also you can treat like your controller as a proxy. So you could be sort of consuming the feed, filtering it further, doing arbitrary transformation logic and serving it, or you can just sort of serve it directly. So basically those ecto queries, which do have limitations, we don't support the whole functionality of ecto queries in the shape definition, but the ecto query in the shape definition basically does the sort of first filtering to get you like filtered tables, and then you can do arbitrary filtering in a proxy layer, and then those, if you're using something like TanStackDB, the power of this cross-collection live query model is that you can then do joins and complex queries to kind of denormalize the data in the client. So it's all, I mean, one thing is it's all just HTTP and JSON. So if you want to like stick a proxy through it, run it through a controller, read it, transform it, you can just do it. It's all sort of extensible.
Great. Okay. So I'm not seeing any questions. I don't know if the app's not working or something. Yeah, let's give James another big round of applause.
Thank you.